Hey, what's up everyone? Jason Turley here, and today we're going to do some more PicoCTF. We haven't done this in a long time. I can't remember the last PicoCTF video that we made for this channel, but today here in the binary exploitation category, we have an easy challenge called Pi Time with a description that reads, "Can you try to get the flag? Beware, we have pi," in all caps. So it might be some type of acronym. I don't think it's talking about like the pie that we like to eat and stuff like that. Additional details will be available after launching your challenge instance. So we can go ahead and do that. And we can also click on the hint because there's no shame in looking at hints. This is all about learning and growing and becoming better cybersecurity professionals. So I don't see any shame personally in looking at hints. So can you figure out what changed between the address you found locally and in the server output? Okay, we don't have enough context to know what that means yet. So we started the binary, or we started the challenge rather, and we do have this netcat connection line to connect to the server that's hosting the challenge. And then we also have the source code that we can download here, and the binary itself can be downloaded here. So just hovering over it, this doesn't show up on camera, but this is a vulnerable.c file. So this is C source code, and then this other one is just the challenge binary. I'm gonna go ahead and just grab the challenge binary and download that, simply because I want more experience reverse engineering, and I don't want to like analyze the source code, which is a good skill to just be able to look through source code and figure out what's going on. But also a good skill is knowing how to use a disassembler or a debugger and kind of step through and figure out what's going on by just looking at the assembly. So I have the vulnerable file here. Hopefully this is large enough to read. If I run the file command on it, we see it's a Linux 64-bit ELF file, which is the standard file format for Linux. That makes sense. It's dynamically linked, so all of the libraries it needs for like libc and printf and things like that are going to be on the system. It's not going to be shoved inside the binary, which is fine. It will be less for us to reverse engineer. And the binary is also not stripped, meaning it still has some of the debugging info and function symbols that will make looking at it a lot easier. So let's just run it. Address of main, and we get this hex address here, and then enter the address to jump to, example OX12345. So what happens if I just slam in uh, this main address? It says your input was this, address of main. Okay, so it just takes us back essentially where we were. What if I just do leap? We get a segmentation fault. So it looks like it is actually trying to jump to whatever address we give it. And since this is not a valid address, it just segfaulted. Okay, I reran the binary, and now we have a different address completely. It looks like the end is the same, 33D. So what if I slam this in and just instead of D, I put E? Okay, we're still here. And what if I do an F? This time I get illegal instruction. Just for laughs and giggles, let's run it one more time. We see this address has changed again, but it always ends in 33D. That's very interesting. So if I do a check sec of this binary, I think I have this installed, check sec of vuln, we can see some of the security mitigations that this binary has. And one of them, pi, it is enabled. So pi is an acronym. It stands for Position Independent Executable. It means essentially the binary can be loaded at different base addresses. However, the offset can be the same. So we saw the offset always ended in 33D. So that will always be the case. However, the base address of the binary will be different every time we run it. If you're familiar with ASLR, address space layout randomization, it randomizes the base address of library calls and like libc and stuff like that. And so printf and system and exec will be at different addresses every time that program runs. So that's very similar. And I don't think we need to really worry about NX or anything else. There is a stack canary, but it doesn't look like we need to do any type of buffer overflow. It looks like we need to provide it the address of some type of like win function or something like that, but I'm not sure yet. So I'm gonna take the time now to actually open up a disassembler. I'll be using IDA Pro. You can use any one you're comfortable with. We're just going to click on new, and then we're going to come over here and just open up our binary. Automatically, IDA picks exactly what architecture it is, so we can just leave all of these as the default and click OK. It's going to take a little bit of time to analyze this binary, and it will automatically load us in here at the main function. So whenever I like to do reverse engineering, I don't want to just read every single assembly instruction line by line. We'll be here all day. I like to take a high level approach. So one thing I like to do is just look at the strings. In IDA, you can do view, open subviews, and then strings. Here we go. Let's crank up the font to size 20. Hopefully this is large enough for the guys in the back to see. But these are the strings that are loaded into the binary. So we see some function calls here. We see fopen or file open. We see signal. So a signal is something like an interrupt, like hitting Control C, for example. So there might be some type of signal catcher for some reason. We see printf. We see standard out being used. What else do we see? Oh, we see segfault occurred, incorrect address. We see U1 and we see flag.txt. Okay, so that's interesting. So let's look at the imports next. The import is the functions, the library functions that this binary will be using. Okay, maybe nothing too useful here. We could have like assumed that it was going to use puts or printf and fopen to print out the flag. We see a call to exit. I'm kind of curious why they're using signal, why there's some type of like a signal handler here. It doesn't really seem necessary for this. But here we go in the exports tab. These are the functions that the binary provides. We can safely ignore all of these ones here that have like underscores in front of them. We're really concerned with this function here that looks interesting called win. And we already know about main. And if we highlight it and look here, there's that 33D that we saw earlier. So the full offset, offset is 133D. So let's make note of that. And we also have this win function that's at offset 12A7. So let's come back here to our IDA disassembler view. And let's just peruse the main function. We have a segfault handler being set up here. So I guess this is what's being called when a segmentation fault occurs and we try to access some invalid memory. That's when it will print out the string segfault occurred, incorrect address. So let's kind of just keep scrolling down. We see some of these strings that were printed when we ran the binary before, address of main, and then we have this format string or this placeholder. Enter the address you want to jump to. We can keep scrolling, and then it prints out our input. And then we see here this call to RAX. So we can assume that RAX is going to store whatever address that we put in, and it's going to try to jump to that address or call it. So we can give it the address of a function. And over here, let me move this so you guys can see. Over here, we have this functions pane, and I can kind of just scroll through and look. And since this is a binary that is not stripped, it still has all the symbol names. So I can click on this function called win, and we can figure out what this is doing. There's a string that just says, hey, you win. And then we see this call here to fopen or file open. If we go one line above it, we see RDI, the first argument, the first parameter. It contains the file name flag.txt. It's being opened in read mode. Assuming that call was successful, we're going to take this branch here, jump if not 0. Looks like it's reading from a stream or getting every single character with fgetC. And then it's printing that out, and then it's closing the file. So we want to somehow access this. We see a few different ways we can get this offset. Let me expand this. Right here, we see the offset of win is 1 to A7. But let's say we didn't have any of that. Something else we can do is come here in IDA and go to options, click on general. And then underneath display disassembly line parts, click this option, this checkbox line prefixes. We hit OK. And now it actually shows us what offset all of these instructions are at. So if we wanted, we could set like a breakpoint in a debugger. That could be useful in a different challenge. I don't think we need to do that. So we need to remember a few addresses. We need to remember this offset 12A7 and 133D. But I think we have enough info to actually solve this challenge. So we can close out of IDA. There's no need to save it. Let's do an LS. Let's showcase a few different ways to do this. Okay, let's see how we can solve this challenge. Let's run vuln. So we have this address here. Let's just make a new tab in tmux. Open up our Python 3 interpreter. So we can get the base address of the binary by taking the address of main and subtracting hex 133D from it. And we're going to get this big integer. I'm kind of curious if I just slam this integer in, would this work as expected? Or actually, I don't want to slam that in. So this is the base address. If we want to convert it to hex, we can, just like this. And we want to add the offset of the win function. And we get this integer. I'm curious if I can just throw in an integer here, or does it have to be in hex syntax? Okay, so it is trying to jump to this address, which is not valid, and it did trigger that segfault handler. So let's actually do this again. Clear, just Control L, subtract hex 133D, and then add hex 12A7 to this, and then get the hex of that. We could probably do this all in one line if we really wanted to. Let's grab that and throw this in here. And it says, hey, you won, but we can't open the file because there is no flag.txt here. Okay, very interesting. So that is how you solve this challenge, but we can do better. So let's actually see if I can do it like this. Let's create a Python file, and we're going to try to solve this using pwn tools. So from pwn import all, the address, or we need to create a process, a handle to the process rather. Let's do p.read until. Right here, address of main, and I'm going to grab this space as well, and let's slam that in there. And let's do a p.readline. So right now, the read buffer is right here. So if I read this entire line, I should just have the address of main. And to prove that, let's do a quick main adder. And then we can print that out. Address of main is this. And we can also print out the type as well. Let's just do a type main adder. Save. Python 3 solve. All right, cool. So we are able to get the main address. It's a byte right now. And then we also have this new line character. So let's come over here and let's actually clean this up a little bit. So let's do a dot decode and a dot strip. This will turn it into a regular string. And from before, we know the main offset is hex 133D, and the win offset is hex 12A7. Awesome. So we know we want to get the binary base address, and we can do that by taking main address and subtracting the main offset from it, just like we did before. So we'll say base address equals that. And this might not compile or work successfully. Right now, this main address variable is a string. So we want to convert this to an integer. and base 16 for hex. Let's print out the base address. Save and run this, see if this even is working or we get some type of error. So here is the base address. We want that to be in hex for when we send it. So let's just try this. All right, cool. So we have the base address. All we need to do now is actually get the win address. So win address equals the base address plus the win offset. So now we can do a p.send line after and just grab all of this up here, including that space, I guess. Slam it in and then do hex win adder. And then we want to print the response. So print p dot read. Oh my gosh, can't spell. Read all dot decode. Let's see if this works. I'm gonna make a dummy flag.txt. So please subscribe. And let's put that into flag.txt. Now let's run our exploit. There we go. So it comes through, it grabs the base address of the binary, it sends our input, and then it prints out U1, please subscribe. Sweet. So now we can come back to the CTF instance and click this button so we can get that netcat line. And we can still do this using pwn tools actually. So let's come back to our exploit. I keep calling it an exploit. I guess it's really not. It's just like a Python script. Let's see if I remember the syntax for this. I think it's just p equals remote and then the host name and the port 60512. Let's save that. And now let's run it. And there we go. It printed everything out and we got our flag. Basic position independence. Sweet. So we can come back here and we can submit our actual flag. And that's it. Hopefully that was entertaining. Hopefully that was useful. We probably could have just done this a lot faster, but I wanted to kind of showcase pwn tools and using IDA. And we did have access to the source code here, but this is a learning environment. These are capture the flags. It's not live, so there's no like benefit of doing them fast. So I did think it's good to take a step back and just look at the assembly and get used to just reverse engineering a binary. So that's it for this video, guys. Next time we'll check out PyTime number 2. It looks like there's another addition to this. But as always, take it easy and I'll see you in the next video.